These last couple of weeks of Chem 104, as I mentioned in the last lecture video, are really about getting you all ready for taking A&P. So this is really just kind of a really quick primer these last couple of weeks, having to do with topics that are kind of important from chemistry that are going to translate over into A&P. So one of the things we talked about last time is the meaning of organic chemistry and what organic chemists study. So we talked about the fact that it's made up of a bunch of different carbon compounds. We talked about the fact that carbon likes to bond 4 times, and then oxygen likes to bond 2 times, nitrogen likes to bond 3 times, and then hydrogen likes to bond, everybody say it, 1 time. So the idea is if you kind of have those rules as kind of a really loose set of guidance, you can come up with a whole bunch of different ways that those things can kind of come together. And that gives rise to this thing called functional groups. One kind of oddball thing that you probably have noticed if you did the warm-up is that the warm-up had to do with something called polarity, right? And not anything to do with these functional groups. So what I thought I'd do with this is to kind of just show you some of the most important functional groups that you're all going to be seeing in biological systems, A&P. And kind of learn how to recognize them really quickly. There'll be a functional group guide that's available that it lists off all kinds of different functional groups, but the ones I'm going to highlight here are all going to be important to you guys in A&P. And so what we're going to do is we'll kind of build that polarity discussion as a part of this functional group discussion as we kind of go through the presentation. One of the most important things to recognize about functional groups are those that are built around this kind of, not really a functional group, but kind of a method of bonding here. This is called a carbonyl group, and if you look at the functional group guide, you'll see a whole bunch of the different functional groups that are present in biological systems that involve this thing, right? And so keep in mind, right, oxygen likes to bond 2 times, carbon likes to bond 4 times. Well, if you put a double bonded oxygen to a carbon, it turns out that that gives rise to the possibility of a bunch of different groups out here, and that really gives rise to the majority of the those types of groups in organic chemistry that are going to allow us to do certain kinds of chemistry and biological systems and stuff like that. And so let's start by just writing this on the board. So this guy is called a carbonyl group. Or I guess it's more carbonyl functionality. It's not technically a group. And so depending on what is to either side of this carbonyl group, we've got a whole bunch of different possibilities that I'll highlight for you right now. So if we start with our carbonyl group and start just putting in different groups out here, I'm going to highlight, like I said, a couple of the most important ones. And so it turns out if we put what I'm going to call an R group, which I referred to really briefly in the last whiteboard activity. It turns out anytime you see an R in organic chemistry, really that means that we've got any number of possible groups out there, but normally it involves some sort of carbon-based group. So if you just imagine anywhere I put an R, there's just a whole bunch of carbons attached there. So it turns out if you have a carbonyl group with some sort of carbon on this side, and you very specifically put an oxygen that's bonded to 2 different things, one is that carbon, one is another hydrogen, this gives rise to a group that is called the carboxylic acid group. And you're probably not going to be surprised to figure out that what carboxylic acids are really good at in the body are acting as acids. There's, of course, other things that are really important, which I'll highlight in just a second, and it'll definitely become a lot clearer as we go through the very final weeks of video lectures here, where I'll actually talk about the different bioorganic polymers that the body is made up of. But carboxylic acids really specifically have the ability to donate this proton. And I know acid-base chemistry is kind of stuff that I've referred to kind of secondarily throughout this course. If you're unlucky enough to take Chem 105, we're really going to do a deep dive on acid-base chemistry, and you'll learn what it means really to be an acid. And it really comes down to the ability to just give a proton away, right? That H with its plus charge. So that's, it turns out, something that this group is really, really good at. So as I said, when you look at that idea of polarity, that idea of polarity really comes to play in that because I've got these two very, very electronegative groups, and you've probably read about electronegativity if you did the reading for the polarity lecture, but I really think about certain atoms kind of have this ability to pull electrons in a covalent bond kind of onto themselves. Like we know that, for instance, these two electrons right here are shared, but the fact that oxygen's such a good puller, it really results in this oxygen being, partially negatively charged. And this carbon ends up being, as a result, partially positively charged. And so one of the things that's going to be a really common theme in A&P and classes like that is this idea of being either hydrophobic, which is water-hating, or hydrophilic, which is water-loving. Turns out carboxylic acids, in terms of solubility in water, they tend to be pretty soluble, right? And it all has to do with that really, really, really strong pull of oxygen on carbon's electrons. And we end up with this really, really water-loving thing as a result of the fact that you've got that separation of charge, because like dissolves like, right? Water really has a really nicely separated positive and negative charge. In fact, a carboxylic acid really looks like water, where you've taken one of the H's of Mickey Mouse and replaced it with this big giant organic part. So if you happen to see this in any kind of structure, it usually gives rise to a really hydrophilic type of environment, right? It's something that really likes to be near water and interact with water. And then possibly in a future lecture, we may talk about a couple of the intermolecular forces, one of which is hydrogen bonding. That's going to be a really important concept when you guys get into A&P. Anytime you see a carboxylic acid, it's really going to be a perfect example of where hydrogen bonding can occur between itself and water, which really adds to the how hydrophilic something is, or how much it really loves being around water. But that's a little bit beyond what I wanted to mention here. So one thing that I did want to say about carboxylic acids is that not only are they just acids, but they're also very reactive. So what we're going to see in biological systems is this idea that we're going to have this like big giant organic-y thing with a carboxylic acid on the end. And it's going to be able to react with a couple of other groups, which I'll highlight up here. And by reacting with them, you're going to end up extending the length of your carbon chain, right? Keep in mind, that's one of the cool things about organic. You have this like huge long chain that it turns out, through a couple of different linkages, often involving a carboxylic acid reaction, are going to be able to kind of link these different chains together, right? And that's actually what happens in a whole bunch of different systems. So bear with me. So let's say I start with my carboxylic acid. And I put another functional group up here, which is called an amine. An amine, at least the simplest kind of amines, are the system that has a nitrogen somewhere, and sometimes it's connected to a couple of hydrogens, sometimes it's not, right? Sometimes there are other R groups, and some sort of R group. Keep in mind, an R is just some big giant organic chain, right? Just think about it as a carbon with a whole bunch of other carbons attached to it. So it turns out, if I take this thing called an amine, and I draw it a little bit differently here, I'm going to erase this too, and I'm going to highlight exactly one of the hydrogens. It turns out that this can give me a little clue into the reactivity of these two different groups. Turns out carboxylic acids and amines tend to react. And if you heat them up, they react in a really, really specific way. So what we're going to talk about happening here is that really what you can imagine happening in a reaction between a carboxylic acid and an amine is almost like it really wants to form water, right? You can see here that I picked out an O, an H, and another H. So if I kind of suck the H2O out of this thing, right? And so let's just draw an arrow and say that H2O just left. And you keep track of both the amine and also the carboxylic acid. the act of doing this, in a sense, makes these two ends kind of sticky and want to stick together. And so what we can do, if you kind of keep track of all the different parts here, and I guess I have to write it down here a little bit smaller, is I'm going to keep all the parts that I haven't touched, right? So this chain, the carbonyl group, in this end right here being sticky, is really going to want to attach to that nitrogen. So let's do that. And everything else gets carried through. And what you'll notice is, as a result of me ripping water out of a system, I've actually created an entirely new functional group. You'll notice that it really is very similar to a carboxylic acid. It's just that on one side I have a carbon group, and instead of having an OH group like I did before, now I have an N with some number of other carbon-containing things. It turns out this is a really important group to biological systems. This thing is called an amide group. Those of you that have had any kind of biology class before, every field calls things a little bit differently, unfortunately. Turns out that this is also called a peptide linkage, right? So this kind of thing, right, when you have a carbonyl carbon next to a nitrogen, right, that's called a peptide linkage. Peptides are one of the very, very important groups that we'll talk about next week in biological systems. Turns out that those are the way that proteins are all put together, right? So anybody that's ever hung out with a muscle head for long enough, eventually they start talking about peptide synthesis or protein synthesis. Gotta get big muscles and get my proteins built, right? Turns out that's exactly what you're building when you build muscle, right? You're actually taking certain biological compounds that have amines, you're reacting with them with a carboxylic acid, and you end up with amides as a result. And as you string this together, right, that's where you get swole. You get those huge pipes, right? Or however the cool kids are calling them now. So this is a really important group that we'll talk about a lot more next week. And it can come from an amine and a carboxylic acid. And one of the things that's really common in biological systems, think about the fact that you're just made of water, right? That's a primary component of what you are. It turns out that water is really a mover and a shaker in a lot of these biological systems, right? The fact that I take water out of something usually joins things together. That's called the dehydration synthesis, right? And that's something that's going to be important in A&P, at least during the week or two they talk about chemistry. Even though you can tell them it's really all chemistry. Shh, I didn't say that. And then also, if you wanted to say digest something, right? I just went out and ate a steak and I want to take some of those organic compounds out of the steak and be able to use them for myself. What can be done is you can actually add water to an amide or amide and actually end up with your carboxylic acid and amine and, join that together with another carboxylic acid and amine. So it's pretty useful to imagine water as kind of the thing that is really bringing things together by leaving or cutting things apart by being added. That's, by the way, called hydrolysis, if you cut something apart with water, right? So if I added water with a little bit of acid here, I'd eventually end up with my amine and carboxylic acid back. So going back to our carboxylic acid, let's take a look at another kind of functional group that is highly reactive with carboxylic acids, and that happens to be alcohols. If you look at your functional group guide, you'll notice that alcohols have a pretty similar structure. The only difference is here, pretty similar structure to amines, right? It's just that instead of having a nitrogen present, you have an oxygen bonded to an H, right? And so this group is called an alcohol group. And obviously that R can be all different things. You could have, like, for instance, ethanol, which is, one of the things that my uncles really, really like, is really just a CH2CH3 out here, right? And so in the body, you have all kinds of different alcohols, right? My uncles have plenty of that type, but the rest of us have other kinds of alcohols in our body. right? And if you kind of keep in mind that like water being a mover and a shaker in a lot of these biological processes, if I just kind of rewrite this alcohol a little bit, you'll probably see a little bit of where I'm going. It turns out that if I do similar to what I did before, and I take an equivalent of OH, right, which is going to liberate water, I can form an entirely new functional group, all based on this carbonyl looking thing, where there's some sort of carbon group on one side, my carbonyl group, and then, just like before, the result of me taking a water out makes these two ends sticky. When those two ends become sticky, you end up with this entirely new functional group, which is called an ester, right? Or a carboxylic ester. There are different types of esters, but this one is the most common one. We'll just call it an ester. You can see what's important there. Once again, we've got a carbonyl group. On one side is some sort of alkyl chain or big giant chain. And then on the other side, you've got an oxygen, just like you did in carboxylic acid case, but now instead of it having B and H, it's actually an R group or some other chain, right? Turns out that you've probably heard of, say, polyester, right? Which is probably what this shirt is made of. And if I ever catch on fire, the reason I'll die very quickly is some sort of flaming pyre. So those polyesters, what they are these repeating units of these ester linkages, right? Where there's an ester linkage here and an ester linkage there. But it turns out in the body, this kind of ester linkage is really important in fats and things like that. They are kind of what hold fats together, these ester linkages. Another name for ester linkages, it's organic, there's 7 different names for everything, is called an acyl group. So you might have heard of like triacyl glycerides and things like that, in different biological classes, maybe not, who knows. But take my word for it, that'll be another important group. And interestingly, if I were to like eat a whole bunch of fats and things like that, if I wanted to take those units and either use them for energy or build other things, my body, right, would metabolize that by adding water. Right? That's that whole idea of hydrolysis, right? We could add water here, we'd get our carboxylic acid and alcohol back, and then we could reuse it in some other way. Again, water is kind of the mover and the shaker here. So there are a whole bunch of other functional groups that we could talk about, but that's something that I'm going to kind of keep for like Chem 106 or for other classes for you guys to figure out. The ones I just highlighted are really the most important ones in biological systems. So what I wanted to do is kind of staying on that theme of biological systems. I wanted to show you something about polarity, which was about what that warm-up exercise was all about. And so this is what I was trying to kind of show you guys, is if I pick out some sort of biological system, right? So let's do a fat, just because we just talked about the triacyl glycerides, right? Well, let's make it let's make it specifically, kind of a semi-fake one here. Okay, so here's a special kind of what's called a lipid, and we'll talk about these a little more specifically next week. And I have kind of taken a little bit of artistic license and I've made it a little bit easier to draw on the board. Normally in a normal lipid, by the way, this is called a phospholipid because it's got a phosphorus and a couple of other crazy groups that we'll talk about next week. But usually these things called fatty acids are much longer. And I wanted to kind of refer back to this idea of polarity. And kind of show you what I mean by that and why it's really important in a biological context for anybody that wants to do really well at A&P. So first of all, one of the things that you might have heard about if you were ever in a biology course before is that these phospholipids have both a hydrophilic and a hydrophobic part. And it turns out that water-loving or water-hating has everything to do with how many different carbons you kind of have connected together, right? It turns out that because these carbon compound or these carbon linkages, right, C's and H's or C's and C's, it turns out that there's not a really good pull on those electrons between a carbon and a hydrogen. It turns out it's just kind of like, you know, watching a tug of war between Pee Wee Herman and another Pee Wee Herman. It's really not that exciting, right? You just kind of watch like, right? The tug on the electrons is not that great. And so what really matters about that is that there's no charge separation, right? There's no plus and minus. And what I like to think about, just because I like to think about being 12 and watching Paula Abdul's videos, I know I'm an old fart, is that like opposites attract, right? That's the way that things are, things are attracted to water through the what's called the dipolar interaction, right? Slight positive charges and slight negative charges really want to get together. If you just have this big giant chain of carbons and hydrogens, it's considered what's called non-polar, right? So let me write that on the board and we'll kind of talk about that a little bit. So lots of C and H. In other words, a carbon chain that has a whole bunch of carbons and hydrogens and not much else, that's going to tend to lead towards what's called non-polarity, which is not a Paula Abdul, right, opposites attracting kind of situation. And it turns out because water itself has a separation of charge, water is very polar, it turns out that things with lots of C and H really hate water, right? So another way of saying non-polar is to say that something is hydrophobic, right? Water hating. It has a phobia of water because water is a really polar thing, right? If you look at the structure of water, I'll just kind of put that over here. You'll notice that this is not Pee Wee Herman pulling on Pee Wee Herman, right? You've got this oxygen with a whole bunch of ability to pull electrons onto itself, such that oxygen has this very minus side and also a very positive side. Don't worry too much about these symbols. These are just called partial positives and partial negatives, and these special arrows are called dipole arrows. I think I asked about it in the warm-up. But anyway, the fact is that if you have a partial positive and partial negative, you really are attracted to positives and negatives, either in ionic compounds, right, which are reasons why like salt will dissolve and like electrolytes are really important in the body. But also you tend to interact with other really nice polar parts of compounds. So like for instance here, these are pretty polar right here. This guy, right, because he's got so many oxygens, that tends to be very polar. That tends to be very polar. But look at this group out here, right? This group out here actually has full-on negatives and positives. So it turns out that this thing, this side, right, if you're very polar, so let's put it this way. We'll say lots of O and N, because they're really strong pullers on electrons, leads to polarity. Right? And you probably can tell where I'm going with this, is if you are considered polar, right? Here we were non-polar and called hydrophobic, right? Water hating. So lots of O and N leads to polarity, right? And so polarity is called hydrophilicity, or you tend to be very hydrophilic. Is it hydrophilic? Hydrophilic? I can't remember how to spell that, but you get the idea, right? And so really what you have in this phospholipid is you've got this very polar region, right, that really wants to be near water, right? So maybe this whole thing, right, that really wants to be near water. And then you've got this hydrophobic region, which really wants to stay the heck away from water. And so what we're going to learn next week is this is kind of the basis of the membrane around cells, right? Really, when you look at a cell, like a biological cell, it has this like greasy envelope made up of kind of the hydrophobic parts. And then on the outside, the one that faces the outside compartment of water and also the inside compartment of water, you have all these different hydrophilic groups. That's kind of what I'm trying to get at by giving you this kind of like shortened version of both polarity and functional groups, is being able to look at a molecule in your A&P class and kind of be like, that guy is pretty polar. He's probably going to, interact with water, or he's going to be very soluble. And just a little bit of an idea of when you look at like a nitrogen bonded 3 times, what are some different options for those 3 different bonds? And what are some like really quick kind of bits of information I can get out of, like understanding a little bit about organic structure. So hopefully this video was helpful. I hope you guys enjoy Thanksgiving, and don't eat too many lipids. Forget it. Go eat some pumpkin pie. Eat your lipids.